Today we're looking at the problem minimum time to visit disappearing nodes. This problem was featured in Biweekly contest 128, and it's a pretty interesting problem about weighted graphs and shortest paths. So the problem reads, we're given an undirected graph of n nodes. We're given a 2D array of edges, where edges I equals ui, vi, length I. And this describes an edge between nodes u and v with a traversal time of length I. So you can see in our example here, we have 0, 1, 2. This represents an undirected edge between 0 and 1 with a cost of 2. Additionally, we're given an array disappear, where disappear I denotes the time when the node disappears from the graph. So you see we have n equals 3 and our disappear array, which also equals 3. This represents the time that these nodes are going to disappear from this graph. For 0, we have time 1. For 1, we have time 1. And for 2, we have time 5 that these disappear. So what we want to do is return an array noting the minimum number of units of time required to reach each node from 0. So we see our output here. We see that our first element is 0. And that's because from 0, it takes no cost to reach because we're already there. For 1, it's -1. And this is because 1 disappears at time 1, but the shortest way we can get to 1 is with this length of 2. So this becomes -1. To get to 2, the shortest path takes 4, but this node disappears at 5, so we're able to get there in time. And we return this as our final result. So when we see a weighted graph like this and finding shortest path, we should immediately think of Dijkstra's algorithm. So Dijkstra's is an algorithm that helps us start from a root node of a weighted graph and find the shortest path to get to every other node in that graph. So we start at 0 with a cost of 0. And we'd put this in a max heap, or sorry, a min heap rather. So what we would do is we'd have this node 0 and 0. So this 0 represents the cost, and this is the node. And what we want to do essentially is process this node, and when we see a node for the first time in this algorithm, we know that this is the shortest path possible in this graph to get to that node. So we'll see we have 0, and we can keep track of the shortest we've seen. So 0 will be 0. Then we would go through all of 0's neighbors and say, okay, now our heap looks like this. So we can get to 1 with a cost of 2, and then we can get to 2 with a cost of 4. So here we see, okay, 2, this is the first time we've seen 1, so we know that the minimum path to get to 1 is 2. So we can record 1 being 2 here, and so on and so forth. Basically, we're going to use this heap to put edges in, and then when we see an element for the first time, we know that this is the shortest path, and we can record it as the shortest and then not process that node again later on. However, there's a slight variation that we have to consider here. So you'll see we added this 2 into our shortest recording. But this is actually not valid, because if you look at the example, we'll see that node 1 actually disappears at 1. So this should be -1, because no matter what, we can never get to 1, because our shortest path would be 2, but because it's disappeared here, we cannot get to it. So what we're actually doing in this problem is using this template of Dijkstra's algorithm, but with one other change. What we want to do is say, take this minimum cost edge, but we also want to consider if this cost is greater than the disappear time we see for that node. So you'll see here, that we're looking at node 1, and the minimum cost to get there is 2. So you'll see that's greater than this 1, which means that there's no possible way in this graph that from 0 we can ever reach 1 within this amount of time. So when we see this, we know this is not valid, and we can just pop it off our heap and continue processing. So essentially what we're going to do, we're going to use Dijkstra's algorithm implemented with a min heap, but we're also going to add in the condition that if the cost to get to a node is greater than the time that it disappears from the graph, we don't process it, and we're going to have the answer for that particular node to be -1. So as for the time complexity of this algorithm, it's going to be O of V times log E. And what this means is that we're going to go through every node in the graph, but for each of these nodes, we're going to place those edges inside of our min heap. And that operation usually takes log of n. So basically we're doing this for the number of edges for each node. So for each node, we're going to go through all of its edges, insert them into the heap, which is a log of E operation. So let's hop over to the code and I can show you how this works. So the first thing we're going to do is set up an adjacency list to make this graph a bit easier to work with. So we're just going to use the default dict here, and then for each edge, go through and add that edge into our graph. Then we're going to start two variables. So we have shortest, and this represents for each node the shortest path that we have seen from 0. And we're also going to start our min heap. And what this is going to be is just starting with one element, where this first element is the cost to get to this node, and this value represents the node itself. So while our heap is not empty, we're going to pop off that element. So then we check if we've already seen this node and it's in our shortest, that means we've already found a shorter path. Or if the cost to get there is greater than the time that it would disappear from the graph, we just continue and we don't process it. Otherwise, what we want to do is say this is the shortest path to get to this node, so we're going to record that in our shortest hash. Then what we do is say go through all of the neighbors of this node. If we have not seen this neighbor yet, we're going to push it into our heap to process later. Then what we do is we're going to go through all the nodes in the range n. And what we're doing here is saying if we haven't found any path, let's just notify that in our hash map and say the path to get there is technically infinity, which means that there's no way that we can get there. Then we're going to create our answer array. We're going to go through all of the elements in our node. We're going to append those and -1 if there's no valid answer, and then return. And let's submit and see if that works. So it does work. Hopefully this was helpful and you learned something. Thank you for watching.